So in a previous video, we talked about taking the inverse of a 2 by 2 matrix, and we had to compute the determinant. So we're just going to revisit that a little bit now. How do you take the determinant of a 2 by 2 matrix? So let's say we want the determinant of this matrix, 2, 3, 4, 5. So to take the determinant, we're going to multiply the main diagonal, and we're going to subtract the product of the other diagonal. So it's 3 times 4. So we get 10 minus 12, and we get negative 2. So the determinant is negative 2. So what that tells us, since the determinant is not 0, we know a bunch of stuff. We know that the matrix is invertible. We know it reduces to the identity. We know the columns are linearly independent. We know they span R2. We know the rank is 2. We know the nullity is 0. If we set this equal to 0 and solve for x, if we solve ax equals 0, we would know that 0 is the only solution. The trivial solution is the only one. So we know all that stuff just by knowing that this determinant is not equal to 0. So let's do another. Two, 3, 4, 6. So I just change that 5 to a 6. So again, we multiply the main diagonal. 2 times 6. We subtract the product of the other diagonal. And we get 12 minus 12. So this is equal to 0. So that tells us that this matrix will not reduce to the identity. The columns are not independent. It's not going to span R2. And all that stuff that I said before, all that stuff would not be true. So now, how do you take the determinant of a 3 by 3 matrix? So we're going to do something a little bit different. It's called Cofactor Expansion. And we need a reference matrix. I called it a sign matrix. You're going to put a plus sign in the top left corner, and then you're going to alternate signs all the way through the matrix. Just alternate the signs back and forth. This will help us get this determinant right. Now, you want to pick a column or a row to do the cofactor expansion along, and it doesn't really matter which column or row you pick, you're going to get the same answer. But some columns or rows will be easier to calculate the determinant for. I'm just going to pick, for the first one, I'm just going to pick the second row, just to show you the difference between a bad choice and a good choice. So I'm going to start out, we'll say the determinant of A equals, start out with that first entry 2, and I'm going to look over in my sign matrix and see that that first entry is negative. So what that tells me to do is to change the sign of that coefficient. So we're going to start out with actually negative 2. And then you're going to take out that row and that column that 2 is in, and we're going to multiply by the determinant of what's left over in the matrix. So we got 5, 0, negative 2, 0. Okay, so that's the first part. Oops. Erase all this. So now we're going to go to 4. And since 4 has a plus sign in the middle in our sign matrix, we're not going to change the sign. We're going to keep it as plus 4. And we're going to take out the row that 4 is in and the column that 4 is in. Whatever's left over, that'll be what goes in our smaller 2 by 2 matrix. And then lastly, we have -1 here, and in our sign matrix, that entry says to change the sign, so we're going to multiply that by -1, so this would be +1 times the determinant of a 2 by 2 matrix. Again, I'm going to take out the row and the column that -1 is in. Whatever's left over, that's going to go in our smaller matrix. So these 2 by 2 matrices, we can easily calculate the determinant using the previous method, right? So -2 times, here we get 5 times 0 minus 2 times 0. That's all just 0. This is going to be an easier determinant here. 4 times 1 times 0 minus 0 times 0, all that's 0. And then 1 times -2 minus 0. So all this gives us the determinant is -2. All right. So again, we see that this determinant is not 0. So we know this matrix will reduce to the identity. The columns will be independent, and they're going to span R3 and all that good stuff. All right, so let's do the determinant again. We're going to pick a different row or column. This time, let's do the third column. You can see before we multiplied by these coefficients, right? -2, 4, and 1. So the more zeros you have in your row or column, the better, because it's going to knock out those. It's going to knock out those terms. So the first one I'm not even going to bother doing because I'm going to multiply by 0. So I'll just move to the next one, -1. I've got a negative sign in my sign matrix there, so I'm going to change that to +1. And I'm going to take out that row and that column. And what's left over is this. And then the last term, the last one's a 0 as well. So it'll be multiplied by 0. So I'm going to leave that alone. So we see we get, 1 times -2 here for the determinant, and that's the correct one, right? So we didn't have to do all these steps. We could have just used that determinant there to get the answer. So when you're picking a row or column to find the determinant, you want to make sure that you choose an easier one if there is one. So you want to pick one that's got the most zeros or ones or -1s just to make the calculations easier. So let's do this big 5 by 5 matrix. And you can see that if I chose the first row here, it's going to be really difficult, right? I'm going to have these coefficients times 4 by 4 determinants, and then I'll have to break those 4 by 4 determinants down. So I don't want to pick that first row. Instead, I want to pick this first column. Everything is 0 except for the first entry. So the determinant of A will be 3 times the determinant of this smaller matrix. And you get this by eliminating the row or column that 3 is in, and we're left with this matrix that's left over. And again, it looks like I want to pick this first column because it's got a bunch of zeros in it. So I can multiply by 2. So this is 3 times 2 times the determinant. What's left over? I'm going to cross these out. I get this. And that's the same matrix that we did on the previous problem. So I know that determinant is -2, but you would go through the same steps there to find that determinant. So it looks like we get -12. So again, we know that this matrix reduces to the identity.